Fixed on either side of its giant external tank, the solid rocket boosters produced 3/4 of the force required to lift the 800-ton craft from the launch pad into orbit. They fire for just 2 minutes, alongside the shuttle's 3 central liquid engines, blasting the shuttle to a height of more than 30 miles at 8,000 miles per hour.
Columbia's altitude, 15,000 feet.
The SRBs produce more power than 44 jumbo jets at full throttle. When the SRB's fuel is exhausted, explosive charges detach them from the main liquid fuel tank. 3 liquid engines then propel the shuttle the final 50 miles into orbit. The SRBs are the only reusable solid rockets in the world. Support ships retrieve them from the ocean and prepare them for another flight. The SRBs are made of interconnecting steel segments. The aerodynamically shaped nose cone contains electronics for guidance and control, and the booster's main parachutes. The remainder of the rocket is a series of steel casings filled with the solid fuel. The propellant is made of a rubbery compound called ammonium perchlorate. It starts as a thick liquid, which is poured into each section around a giant metal core. It takes 8 days for the fuel to harden. Then the metal core is removed, leaving a tunnel 6 feet in diameter and 120 feet long, through the center of 500 tons of instantly explosive solid fuel. The exact shape of the tunnel through the fuel determines the amount of thrust the rocket delivers. The cavity in the forward section is star-shaped to increase its surface area and give maximum burn. This provides the initial burst of thrust required to lift the shuttle the first few feet off the pad. It is a giant tube of high explosive, just waiting to explode. The rocket uses a type of flamethrower to ignite the fuel. The flame shoots down the central tube, causing an instant explosion. The gases expand at more than 8,000 degrees Fahrenheit. They burst from the rear nozzle at over 2,300 miles per hour, producing the same horsepower as 64,000 V8 cars. But solid rockets have one major disadvantage. Once they have started, they cannot be stopped.
T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Roger, Challenger.
On January 28th, 1986, powered by these incredible rockets, Space Shuttle Challenger lifted its 7 crew members into the skies. Just 73 seconds into Challenger's flight, disaster struck.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
It was the worst accident in NASA's history. All the crew were killed.
We have no downlink.
Falling from a height of 30 miles, the shattered wreckage crashed into the sea for over 5 minutes after the explosion. Somehow, the world's most sophisticated and amazing machine had failed. For months, NASA searched the ocean depths, looking for vital pieces of an impossible jigsaw, hoping for an explanation for the catastrophe. Amazingly, they recovered 45% of Challenger itself and most of the SRBs. They stored the wreckage in a disused warehouse. Then NASA began a detailed examination, uncertain of what they would find. But the investigators had one vital tool to help them: NASA's cameras. Studying Challenger's doomed liftoff, they quickly noticed something unusual. When its boosters ignited, a puff of black smoke was clearly seen emerging from a lower joint. As the shuttle sped higher, flames began licking the side of the giant external tank. The Challenger's solid fuel rocket booster was leaking gases at 8,000 degrees. Examination of the wreckage confirmed their suspicion. The Challenger's right booster had a giant hole burned right through it. But why had the booster leaked? Where the segments of the boosters meet, thick rubber O-rings form a gas-tight seal. NASA's inquiry revealed that hot gas had damaged the O-rings on 12 previous shuttle flights, but with no malfunctions. This time, something was different. It was the weather. On the day of Challenger's launch, the temperature had plunged to just 36 degrees, 15 degrees colder than on any previous launch. Ice had formed on the pad overnight. It had also frozen the booster's rubber O-rings. The freeze made them tough and inflexible. At the moment of ignition, they leaked, and Challenger was doomed.
It's no longer just government payloads. It's now commercial payloads.
Satellite technology has fueled our insatiable hunger for instant communication and up-to-the-minute information from around the planet. And that hunger has initiated a new era in the history of space exploration, the race to make space pay. Each year, hundreds of payloads are sent into orbit. The industry is worth billions of dollars. Rockets are big business. The space shuttle is back, leading the race for the space dollar, despite being grounded for 2 years after the Challenger disaster. Its ability to deliver, repair, and retrieve space cargo is unique. It has carried more tons of payload into space than any other vehicle. The strongest competition is from Russia. They have thrown all their energy and resources into the new space race. This launcher was originally used for Buran, the Russian copy of the American space shuttle. They call this rocket Energia. It stands 200 feet tall. Its 8 engines generate more than 4,000 tons of thrust. This is the most powerful rocket ever built. In 1987, Energia smashed all launching records. It lifted a massive 100 tons of payload, 3 times the maximum capacity of the shuttle, and far more even than the mighty Saturn V that pushed men to the moon. In February 1996, the Chinese attempted to launch an American communications satellite on a rocket called the Long March. Only a few seconds after liftoff, it veered wildly off course and nosedived towards the southwestern province of Sichuan. It crashed directly into a nearby village of several thousand people. Nearly every building was completely destroyed. The death toll of this disaster has never been officially confirmed. In that same year, America's biggest competitor in the launch market suffered a terrible setback because of a simple human error. The Ariane series of rockets successfully launched payloads for the European Space Agency, ESA, for nearly 20 years. Ariane 4 averaged one launch every 4 weeks, offering tremendous reliability to the commercial space transport business. It was the most effective unmanned launch system in the world. In June 1996, ESA unveiled its star attraction, a rocket they hoped would take them into the lead in the launching market. Ariane 5. It stands over 25 stories high. It is a highly sophisticated two-stage rocket. For its first launch, it would carry 40 tons of payload held in compartments in its upper stage. Its main stage contains the largest cryogenic tank ever built, storing its fuel at minus 420 degrees Fahrenheit. It burns 160 tons of liquid hydrogen and oxygen, channeled through just one engine. As with the space shuttle, solid propellant boosters provide the majority of its takeoff thrust, 80% of the power needed to lift it off the pad. They intended it to be the crowning moment in European space history. On June 4th, 1996, Ariane 5 would lift off from ESA's launch pad in French Guiana on her maiden flight.
À tous de les deux, attention pour décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu. Allumage.
On board Ariane 5 was over $6 billion worth of equipment, representing 10 years of international research. Seconds into its flight, it suddenly changed direction and headed for the local town of Sinnamary. As the rocket exploded, hundreds of tons of rocket parts and toxic chemicals rained down on the jungle.
It is very difficult to make a rocket perform perfectly. A rocket is a very complex system with many elements and subsystems, and all of them must work perfectly when required. And in our life, in our business, we either have 100% success or 100% failure. There is nothing in between.
ESA salvaged as much of Ariane 5 as possible, but their investigation discovered that the rocket itself had performed perfectly. The problem lay in the computer code that operates it.
Well, there were basically two reasons for the crash. The first one was that there was a software failure in the inertial guidance system. And the second one was that this failure was not detected during the extensive tests which have been done.
Rockets navigate using inertial guidance systems controlled by onboard computers. Both computer guidance systems on Ariane 5 had failed. The reason was simple human error. Engineers had accidentally loaded computer software from Ariane 4 into Ariane 5. Soon after liftoff, the onboard computer instructed the rocket to turn too quickly, and it veered dangerously out of control. But the computer knew something was wrong, and to prevent disaster on the ground, it destroyed itself in midair.
We're armed, sky's clear, and here we go.
It isn't just professionals who launch rockets into space.
Punch it.
Gripped by rocket fever, each year thousands of enthusiasts launch their own homemade machines, simply for the thrill.
That cracked the sky nice.
That's what it's about. That's the North Star. Flies perfect every time.
These Rocketeers are members of Tripoli, America's largest private rocket club.
Got smoke. There you go.
Each year, amateurs hold more than 70 launch events all over the United States, involving 2,500 club members from all walks of life.
This is my rocket Big Red. My husband gave it to me for my 12th anniversary last year, and I launched it this morning and got it to 2,500 feet and had a little bit of damage on the way down, but it'll fly again, no problem.
The biggest event of the year is held in the Black Rock Desert in Nevada. In 4 days of non-stop action, they launch over 2,000 rockets.
Smoke. There it goes.
But these rockets are not toys. Some can reach heights of up to 100,000 feet. Amateur rocket builders are sending their machines over a quarter of the way to space.
The range is clear, the skies is clear. We're going on 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition.
The enthusiasts make their rockets from kits or build them from scratch. The body is rigid cardboard or fiberglass tubing. Inside, they use solid fuel almost identical to that in the Shuttle's solid rocket boosters. These amateur machines are becoming increasingly complex.
It's slated to go approximately 27,000 feet off the surface. It's carrying several payloads. We'll be recording barometric pressure outside through a port. There's an onboard accelerometer that will be collecting flight information. And then there's an experimental telemetry package that we're flying with.
The rocket builders use computers to monitor and adjust their machines for maximum performance. But like their billion-dollar big cousins, they also have the occasional hiccup.
5, 4, 3, 2, 1. Let's try pad number 7.
I got my camera.
And I still got my sense of humor.
But no matter how their machines perform, for the members of this club, rockets have become a total obsession.
This is carbon fiber, and it's called Thunderchild. After H.G. Wells' War of the Worlds, it's Thunderchild. It's my child. I fly it, and I care about it, and we polish them, you know? Kiss my Katie. Good girl.
For amateurs and scientists alike, space has always been the ultimate dream. In 1963, at the height of the Cold War, Kennedy set the greatest challenge in history.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
To achieve this seemingly impossible task, America turned to a man who just 20 years earlier was a mortal enemy. The father of all modern-day rockets, Wernher von Braun. Von Braun had been Germany's foremost scientist. In 1944, Hitler commissioned him to develop a weapon that could win Germany the Second World War. It was Germany's ultimate secret weapon, a liquid-powered rocket called Vengeance, better known as the V-2. Each V-2 carried a deadly 1-ton warhead. In just a few months, over 3,200 rockets were fired at London. No defense was possible. The rockets brought terror back to the British population at a time when they had believed their enemy was all but defeated. Previous rocket designs had used a single fuel stored in one large tank. When von Braun designed the V-2, he decided instead to use different liquid fuels in separate tanks and mix them together in a combustion chamber where they would ignite at high temperatures. He experimented with different fuel mixtures, with a few spectacular failures along the way. But he succeeded in producing one of the world's most devastating new weapons. Burning pure alcohol mixed with liquid hydrogen, his V-2 rockets traveled faster, longer, and with greater power than any before them. But unlike Hitler, von Braun had other ideas for his machine. When Germany fell, he fled with his rockets to America. The Cold War had begun. Russia and the U.S. eyed each other with increasing suspicion and hostility. They began to develop ever more powerful and sophisticated rockets and missiles. Space was the new battlefield. But the price was high. As the complexity of the rockets grew, so did the risks. 74 Russian technicians were burned to death when a giant R-16 rocket exploded on the pad because last-minute welding had failed. It was the worst accident in space history. The race for military supremacy took a deadly toll. But that did not stop the scientists. The Russians unveiled the largest rocket yet built by either superpower, the Zemyorka. It stood over 104 feet tall. The Zemyorka had 4 giant liquid engines and 16 further rockets in its strap-on boosters. It had enough power to send an atomic bomb over 5,000 miles. But in the end, this red giant delivered a peaceful blow. On October 4th, 1957, a small satellite called Sputnik sent out an alarming message to the U.S. The Soviets had beaten them into space. He was about to become the first human being to enter orbit in the tiny capsule of his Vostok 1. Gagarin reached a height of 200 miles and completed one orbit of the Earth. His flight lasted just 108 minutes. It was the finest achievement in the history of world exploration. As Russian leaders celebrated Gagarin's amazing journey, they knew they had delivered a final blow to America's damaged pride. America responded the only way it knew how, with maximum effort. Just 5 weeks after Gagarin's flight, Commander Alan Shepard became the first American into space. His journey in the Mercury spacecraft lasted only 15 minutes before he landed in the Atlantic Ocean. It wasn't enough. America wanted the greatest prize of all, and they wanted it fast. To reach the moon was an incredible dream. To reach it before the end of the 1960s seemed almost impossible. A job only one man could hope to achieve, Wernher von Braun. Using all of NASA's resources and scientists, von Braun took on his ultimate challenge: to build a rocket powerful enough to launch a manned spacecraft 240,000 miles to our nearest neighbor in space and back. In just 6 short years, he did it. He created the most powerful and complex machine ever built, the mighty Saturn V. Saturn V towered over 363 feet. Loaded with fuel, it weighed 2,800 tons. It carried its precious cargo of 3 astronauts in a tiny capsule in the nose. The vibrations from its first launch were so great that they registered at an earthquake monitoring station over 1,000 miles away. Wernher von Braun had exceeded even his own wildest dreams. Thrust its titanic weight into space, the Saturn V had 3 separate stages. The first stage used 5 kerosene-powered engines, burning over 15 tons of fuel every second. The giant exhaust plume was over 1,000 feet long. But its upper stages set the Saturn V apart from any other rocket before it. Stages 2 and 3 had the first ever engines powered with liquid hydrogen and oxygen. They were the only way for a manned capsule to break the powerful grip of the Earth's gravity. Saturn V traveled 250,000 miles in 3 days and finally delivered its precious payload safely to the surface of the moon. Kennedy's dream had become a reality. In 13 launches, the Saturn V carried 27 astronauts on Apollo missions to explore the moon. Von Braun had built a machine that changed our destiny forever. Saturn V's liquid hydrogen engine was the first, but not the last. Its direct descendants are the engines in one of the most sophisticated machines the world has ever seen, the Space Shuttle.
They tease us with the potential of being able to travel anywhere on the Earth very quickly. They tease us with the future of new opportunities in space.
In the early 1900s, science fiction writers toyed with the idea of a spaceship which would fly, land, and take off again under its own power. They foresaw that the rocket would be transported vertically to its launch pad. In the 1990s, that dream is now a reality.
7, 6, 5, 4, start check engines.
Codenamed DC-XA, this McDonnell Douglas rocket is opening the door to routine and affordable space travel. The DC-XA can lift off vertically under its own power. It has no separate stages or throwaway boosters. It is a giant flying fuel tank. It burns 90% of its takeoff weight in its first 3 minutes of flight. In tests, the DC-XA has flown to over 10,000 feet. It can maneuver and fly in almost any direction with amazing versatility. To complete its journey, the DC-XA performs its most remarkable maneuver. It lands in its original takeoff position on its tail. It can be ready to fly again in just 24 hours. The ground crew control the DC-XA by computer from a nearby trailer. It takes just 15 crew to prepare and launch it. The space shuttle needs more than 30,000. Its secret lies in its super lightweight construction. The oxygen fuel tanks are built in Russia using the lightest of metals, lithium. The hydrogen tanks are made of epoxy, the same material used in bulletproof vests. But after many successful flights, the DC-XA test program finally came to an end in 1996.
Landing small negative. Engine out.
She's coming over.
Okay, we had a gear that was not out.
The DC-XA was never designed to fly into space. But the valuable information gained from the test vehicle has enabled NASA to take a major step toward a new generation of launch vehicles and rockets. Reusable and operate at 1/10 of current launch costs. One day, the Venture Star may replace the aging space shuttle. It will also use a new breed of engine, the most efficient rocket ever designed, the Aerospike.
The major difference with the Aerospike is in the shape of the nozzle. Today's rocket engines have a bell-shaped nozzle. The Aerospike engine has a V-shaped nozzle. The reason we use that shape of a nozzle is to allow the engine to automatically adjust its performance as it climbs through the atmosphere.
In NASA laboratories, scientists are testing a new type of rocket engine, the nuclear-powered ion drive. It generates an electric force field that can produce velocities twice as fast as current rocket engines. To test the ability of the ion engine to endure interstellar space travel, the engine is mounted in a vacuum chamber and run continuously for 8,000 hours, almost one whole year. But rockets of the future will have to operate for even longer and at greater speeds. A design for a spacecraft called Daedalus uses nuclear power in a very different way. It ejects millions of tiny atomic bombs into space behind it, one after another. This starship design could reach 1/10 the natural speed limit of the universe, the speed of light. For the first time, we could explore far beyond our solar system. Other craft may even leave their power source at home. The laser sail is propelled by the power of a laser beam from a base near the sun. The giant 200-mile sail tows a tiny spacecraft at very close to the speed of light. The original V2 flew just a few tens of miles across the English Channel. Today, there are thousands of satellites orbiting above our heads, and people have walked on the surface of the moon. Rockets have already transformed our world. One day, they will take us to worlds we have never even imagined.